All right, welcome back. We're going to talk today a little bit about some statistics that will be important as we move forward here. Those who have had a statistics course, this should be a review. For those that haven't had a statistics course, let me explain a few things that are going to be important. So first off, let's look at this. This is the expected return. So R is going to represent a stock return, and you can think of a return as a percent change in price from day to day or from month to month or from year to year. So this is the expected return, and you can see in practice how this might be useful. It might be useful to calculate what investors might expect to receive if they were to buy a particular stock. And the expected return is calculated, don't get lost in the math here, as the weighted average between pi in the jth economic state and the returns to the stock in that state, where pi represents the probability of a particular economic state occurring. So all I'm going to do, and we'll work some examples, and by the time we're done working these examples, you'll have it down. I'm going to multiply the probability of some economic state occurring times the return of that stock in that state, and then I'm going to add across or sum across the different economic states. In other words, I'm going to calculate the weighted average, where the weights are the probabilities of the economic state occurring, and that's going to give me my expected return. Okay. Let me drop down here and talk about the standard deviation of expected returns. So just like in practice, the expected return will be useful in us evaluating whether or not we're going to get a sufficient return by investing in a particular stock. The standard deviation, denoted as sigma subscript expected return, also provides important information practically to us. It's the square root of the sum of the weighted square difference between the returns for a stock in each economic state J and the expected return that we just calculated squared. So again, I'm going to take the probability pi of the jth state occurring. I'm going to multiply it by the squared difference between the returns in that economic state and the expected return, and I'm going to sum across the states. I then take the square root, and I get a standard deviation of expected returns that is also in the same terms as the expected return. For instance, if I get an expected return of, say, 12%, I could get a standard deviation of 10%. This will be important practically to us here in just a second. We have discussed in the past how difficult it is to estimate or assess probabilities of different economic states occurring. As humans, we're just not good at estimating these types of probabilities. That's all right. If you look here, this squiggly equal sign means that the expected return, if we don't have good probability measures, is best approximated. So that squiggly equal sign is a best approximation for the expected return, is just the arithmetic mean, R bar, which is equal to the sum of all historical returns from I equals 1 to n. So say we grabbed n number of historical returns. These returns could be daily historical returns, monthly or annually historical returns. We're just going to add those returns up and divide by the number of observations. Divide by n. And that number will give us the arithmetic mean, or the average, and that average return is a very good approximation of the expected return. Okay, we're not good at estimating probabilities. The best way we know how is to use historical data, so it shouldn't come as a surprise that using historical data and calculating arithmetic means is a good approximation for calculating expected returns. Likewise, we're going to approximate the standard deviation of expected returns with the sample standard deviation. From your stats class, you'll recall that how to calculate the standard deviation. I take the historical return in each time period I subtract the mean return, I then square it, I then sum up all of those squared differences and divide by n minus 1. That gives me the variance of historical returns. I take the square root, and that will give me the standard deviation of historical returns. It's important to note that the standard deviation is more widely used in finance than the variance, because it puts a number in the same terms as the mean or expected return. Again, if the mean return is 12%, I could calculate a sample standard deviation, and the answer to that sample standard deviation would also give me something in percent terms, say 10%. Okay, so let's talk about what this means conceptually. So here is a graph of a normal distribution. Okay, you'll see this says probability density on the left-hand side, and these are values that we're analyzing. So let's call mu here the return, all right? And let's say the average return is say 12% per year. There's a couple of things to note. This distribution is calculated as the frequency of historical observations. So say we grab 100 months of data. We grab 100 months of data, and we plot the frequency of observed returns in this graph here. That is, we have the most returns that are going to be centered around a mean return of mu in this case, but r bar in the previous case. A couple things to note here. So the standard deviation, sigma, you see here I have the mean return plus 1 standard deviation and the mean return minus 1 standard deviation. And so this tells me that 68.27% of the entire distribution is between -1 and +1 standard deviations. That means, let's say you have a 12% return, mean return, with a 10% standard deviation. That means I have a 68.27% chance of earning between 12 minus 10, which is 1 standard deviation below the mean, so that's 2%, and 12 plus 10 and 22%. So I have a 68.27% chance of earning between 2% and 22%. I hope that makes sense. So the standard deviation is super important because it gives us some inference about what we would expect to earn. Okay. Notice also that I can subtract 2 standard deviations. So if my mean return is 12% and I subtract 10% here and another 10% here, that's 2 standard deviations, right? I have a 95% chance of earning between a -2 standard deviations and a +2 standard deviations. So in the example that I gave of a 12% mean return and a standard deviation of 10%, I have a 95% chance, according to a normal distribution, of earning between 2 standard deviations below the mean, which is going to be, let's see, you're going to take 12 minus 10, that gives you 2, minus another 10, that's going to give you -8%, down here at your lower bound, and 12 plus 10 plus another 10, and that's going to give you 32%. So I have a 95% chance of earning between -8% and 32%. So statistics are important. They give us some ability to make inferences regarding what we should expect to earn if we were to buy a particular stock. Of course, 99.73% is between -3 and +3 standard deviations. So a couple of things here. As the standard deviation is bigger, then this distribution gets wider, right? And the probability of earning between -1 and +1 standard deviation, those values are going to be very far apart. So understand that sigma is measuring a measure of risk, a measure of uncertainty. We call it in finance volatility. So the standard deviation is measuring volatility. And when stocks are more volatile, the distribution of those stocks is going to be wider. So for instance, let's say this distribution represents stock A. If I were to draw another distribution that looked like this and had a much wider distribution, the second stock that I drew would have a bigger standard deviation.